Alright guys, this is it's a equilibrium problem. We're trying to balance this beam. So anytime we're doing balance problems, you'll do something similar to this. We got a beam going across here, and it tells you the length. The beam's about 5 meters long. So the radius of the beam is 5 meters. And then we got a bunch of forces that we're going to look at here. So we got, right, the beam's being supported by this support. So that's an Fn, and I'm going to call it 1. And then they got this support pushing up on it, Fn2. We also have the weight of the beam. And since it's a uniform beam, we'll put that right in the middle. So this is the weight of the beam. And then we got, this is a roof structure. It's also pushing down on the beam, and again, it could be anything. It could be a person. Something's pushing down on that beam. We're going to call that, so we'll call it force gravity of the structure coming down. So there's our 4 forces. It wants to know how much force is being applied to the side supports. So we're actually looking for Fn1 and Fn2. We do know one more thing. We know the distance to the beam, to the roof structure from this support force. So we know this radius, or this distance. You'll see why we're using R in a minute. We'll call it RS, is 3 meters. So we're going to start with forces because that's what it asked for. If it started with radius, this is, so, and we've talked about torque. This is why we're using R instead of the length. We're looking at 2 things. We're looking at the forces coming down on this thing, and then we're looking at the torques balance out. So we're going to balance forces first with the old sigma F equals ma. How many forces are there? There's 4. So Fn1 minus Fn2, plus, because those are up. And then you got the 2 weight forces going down. So the weight of the beam minus the weight of the structure. And then those all, we don't want that to move at all. So we sum that up to 0. We don't want it to accelerate. We can put some numbers in, but you're going to see we get stuck. We don't know the 2 side supports, so those are unknowns. We know the weight of the beam's 9,800. And we know the weight of the structure from above is pushing down with 810. But we get stuck because we don't know the 2 support forces. But now we can do if we translate force to torque, right? Instead of using F, we can use tau. M becomes mass becomes moment of inertia, so it becomes an I. A becomes alpha. We can use this equation. We can sum up the torques to finish this up. So then all we're going to do is add or multiply all these forces by radiuses. So because torque is force times radius. So we got Fn1 times R1 plus Fn2 times R2 minus F, right, the weight of the beam times the radius of the beam minus the weight of the structure times the radius of the structure. And then those also, we don't want that to, we don't want it to rotate. So we're going to sum that out to 0 too. And then we can put, the next step, we got to pick a pivot point, which, let's pick a color that'll stand out. They referenced everything from the first support. So I would pick that as the pivot point. Usually we'll pick it as, we want it to be a point where the radius is going to be 0 and it cancels stuff out. So by picking the first support as the pivot point, I get Fn1, which I don't know, times 0. So it goes away. Fn2, I don't know, but I know it's 5 meters away. And then, I know it's 5 meters away. The weight of the beam's 9,800. And it's a uniform beam, so it's going to act at the center. So half of 5 is 2.5 minus the weight of the roof structure above. That's 810, and then it told us it was 3 meters away. That all has to equal 0. We can solve that for Fn2. All right, and then that gives us 5,386 newtons, 5,386 newtons, which sig fig wise we're going 5,400. I guess I should go all the way down. That 3 meter support's a little off with its sig figs. Here, we'll leave it at 2 though. So 5,400. Then we're going to take this number and plug it back up here, and we can solve for Fn1. Call it a day. Fn1 plus, and then I would just use the calculator number 5386 minus 9800 minus 810. And we can solve this one for Fn1, which is about 5,224 newtons. And then as you get better at these, you can, like sometimes we'll do these seesaw ones. We have a person on this side pulling down, person on this side pulling down. You got the beam, the fulcrum pushing up. Sorry, that's Fn. That's sloppy. And then you got the weight of the beam pushing down again. But if you put your pivot point right there, right, there's my pivot point. These two forces go away. These two torques go away, I should say. The forces don't go away, but the torques go away. So some of these situations you'll be able to simplify them down. You won't always have 4 forces.